So far we talked about the memory layout, anatomy of transaction. Let's talk about how to authenticate the messages in the contracts. And in this lesson, I would like to talk about 4 different categories of authentication. First one would be a simple classic authentication with a signature. As you recall, any event in the TON blockchain should start with an external message. An external message is really not authenticated by itself. It's just a bunch of data that arrives as a message into some contract. And usually, the external messages land in the wallet contracts that belong to each user. So if you look under the hood, what the wallet does is really 3 things. It stores TON coin balance for the user. It stores the sequence number that it uses to prevent replaying of the messages. And it stores the public key. Whenever the external message comes in, it reads off 64 bytes of data, that is the signature for the rest of the message, verifies the signature with its public key, and then treats the rest of the message as the instructions to send other messages to other contracts internally inside the blockchain. So that's really the only job of a wallet. And you may have some other systems where we have a similar pattern where you receive the raw binary data as a message, check its signature, and then process the rest of the data. One thing to note is that this is something that you really want to reserve just for the wallets, because your system becomes more composable and more flexible if you build the rest of the communication between the contracts using internal messages. And this is where the second authentication mechanism comes into play. And the second mechanism is the authentication of a message sender. All the internal messages in TON, they're identified by a message sender that is guaranteed to be correct and secure by the TON protocol. So every time a contract receives an internal message, it knows for sure from which other contract the message was received. And this is immensely more cheap and powerful than checking the signatures. First of all, you're not limited to the humans who could make those messages. You could also plug multiple contracts together in a pipeline. So for instance, you may have a token that has an owner, and this owner is specified not as a public key, but as another contract address. And now in most situations, this contract address could be a wallet address. And this means that the token can be updated, like its owner could be updated by the message from this wallet. But equally, this address could be an address of a multi-signature vault, or it could be an address of a decentralized exchange that owns this token. So really, authenticating your messages by a sender gives you immense flexibility in terms of who could access your application or your token. So how authentication works exactly here? Well, it's pretty simple. In the handler that receives the internal message, you simply check the message sender, and you know that the rest of the network provided you with accurate and correct message sender. So you simply compare it with whatever address you store in your contract state. Let's say you have different roles, admin and manager and operator. And for each of these roles, you have separate slots in your storage and separate addresses. And so you could compare your message sender with one of them to determine which role is triggering this message. So this is much cheaper than checking signatures and much more flexible. So what are the other 2 interesting ways to do the authentication? The third one is building on top of the message sender. Since the addresses in the TON ecosystem are not simply unique identifiers of the contracts, but they're also cryptographically secure hashes of the contract code and data, and more specifically, initial code and data, so they don't change when the data changes. And since those addresses are cryptographic commitments to this code, you could verify what kind of code is talking on the other end by checking the message sender. And this allows you to do something, what I call the DNA check. So if you look under the hood of tokens, and we'll talk about them in the separate lesson, then you will notice that there will be contracts that have identical code but different data, and they communicate between each other. And the way they authenticate this communication is by checking not the exact contract address, but they check that whatever data they have, it's attached to the same code as the current contract has, which means that the contract can trust that the other side, the sender of the message, executed their part of the protocol correctly. So the contract effectively could mix up on its own end some data and the code that they trust, compute it on the fly, and compare it with an actual message sender. And this way authenticate that the sender could have any data and maybe any address, but they have identical code and therefore identical DNA, and then therefore they could trust each other. So this is a very powerful pattern that we'll talk about more in more detail in the next lessons. But this kind of shows you what you can do with the message sender in your own contracts. And finally, the fourth type of authentication is something not to forget about. It is a lack of authentication at all. This is quite interesting. Isn't it insecure to not authenticate the messages? Well, in certain situations, this is where the security actually lies. Let's say you have a system that must be censorship resistant. Let's say it's a decentralized staking pool that needs to do payouts every once in a while. And someone has to trigger the message to start the payouts. If that message was authenticated with a public key or some contract, then this means that there would be a single operator that controls the access to the payouts. And that would be bad from the censorship point of view. Now, what you could do for such a system, you could create a message handler that doesn't do any authentication by design, and maybe protects itself against denial of service in some other ways. For instance, the sender of the message needs to pay the fees for the gas. But we don't really care about the sender, and we allow any computer or human to trigger this message. And this is a deliberate design decision in your application to choose when to not authenticate messages. And think of this as a way to say anyone in the world can be an author of this message. And this is also an important pattern that comes into play if you build truly decentralized applications. So to recap, there are four types of authentication in TON. There are signatures to authenticate external data, external messages from actual humans or systems outside the blockchain. There are authentication by a message sender in the internal messages to differentiate different roles. And this is a more recommended way for complicated contract setups because it's more composable. Third type of authentication is the DNA check, where you compute the necessary message sender address on the fly by referring to the code or data that you trust. And finally, there is lack of authentication at all to provide censorship resistance to your application.